Today we are going to take up a new topic in the class of solid state pharmaceutics, polymorphism. We will learn an introduction about polymorphism, classification of polymorphism, identification of the types of polymorphism, the phenomena of phase transformation. The regulatory aspects of polymorphism will be covered in a separate class. First, let us look at the definition of polymorphism. Polymorphism is the ability of a substance to exist as two or more crystalline phases that have different arrangements and or conformations of the molecules in the crystal lattice. Hence, polymorphs are different crystalline forms of the same pure substance in which molecules have different internal structure, that is arrangements and or conformation of the molecules. The important aspects to remember in this definition is that polymorphs are crystalline in nature. If there are two polymorphic forms of a drug, it means there are two crystalline forms which have different internal arrangement in the crystal lattice. As per ICH Q6A and US FDA, polymorphism is the occurrence of different crystalline forms of the same drug substance. This may include solvation or hydration products, also known as pseudopolymorphs, and the amorphous forms. Another definition of polymorphs defines them as the solid forms of a substance that have a common liquid phase. This would also include amorphous state in the scope of the definition of polymorphism. Although amorphous form is not crystalline in nature, still as per this definition, amorphous form would be included in the definition of polymorphism. Remember, polymorphism is an exclusively solid state phenomena. If you have a crystalline material which you dissolve in some solvent, then there is no relevance of the term polymorphism, because in the solution state, the solid does not exist and the molecular dispersion of the solute in the solvent would have formed. Some important aspects related to the polymorphs are given in this slide. Polymorphs have the same chemical composition. Say if there are two polymorphs of paracetamol, the molecular structure of the molecules in both the polymorphs is going to be exactly the same. Different internal crystal structures, that is different unit cell, due to difference in crystal packing arrangements and or different conformations. Polymorphs have different lattice energies and entropy. They have different physicochemical properties like true density, melting point, solubility, compressibility, and sometimes even color. However, there are no differences in liquid or vapor state. As stated earlier, polymorphism is exclusively a phenomena of the solid state. Examples of polymorphs: chloramphenicol palmitate form A and form B, ranitidine form 1 and form 2, aztreonam alpha and beta form, rifampicin is reported in 5 polymorphic forms. The following are some of the physical and chemical properties that may vary along the polymorphs. Packing properties like true density, refractive index, thermal and electrical conductivity, and hygroscopicity may be different for two different polymorphic forms. Thermodynamic properties like melting point, internal energy, enthalpy, heat capacity, entropy, free energy, and solubility. Spectroscopic properties like FTIR, Raman, and solid state NMR. Kinetic properties like dissolution rate, rate of solution state reactions, and stability. Surface properties and mechanical properties like hardness, compactability, handling, flow, and blending. These are the properties which may differ between one polymorphic form to another. Here is an example of two polymorphs of curcumin. and the two forms are form 1 and form 2 of curcumin. This is the solubility of the two forms in ethanol water 4:6 mixture. As is clearly seen in this graph, curcumin form 1 has lower solubility as compared to the solubility of curcumin form 2. Even the oral bioavailability of the two forms differ. In the same rank ordering, the curcumin form 1 has lower bioavailability, while the bioavailability from the curcumin form 2 is higher. Let us now look at the classification of polymorphism. Polymorphs are classified based on two systems. First one is based on packing and conformation states, while the second one is based on relationship of the thermodynamic properties. As per the first classification system, two types of polymorphs, that is packing polymorphism and conformational polymorphism, is possible, while based on the thermodynamic properties, enantiotropic system and monotropic systems are possible. Let us first look at the packing and conformational polymorphism. Packing polymorphism arises due to different assembly modes of conformationally equivalent molecules. This means that the molecules are having the same conformation in the three-dimensional space, but they have been packed and assembled in different modes. Different packing modes are readily available to compound for which hydrogen bonding is important. Since there are multiple possibilities to achieve the necessary intra and intermolecular forces. Ethyl maltol polymorphs fall under the category of packing polymorphism. This is the form 1 of ethyl maltol, form 2 and form 3, in which the conformation of the molecules remains the same. Only difference is with respect to the packing of these conformationally similar molecules in three different crystal lattices. Different crystallographic features of ethyl maltol polymorphs are captured in this table. Crystal class for form 1 is monoclinic, for form 2 is hexagonal, and for form 3 it is triclinic. These are the space groups, the crystal habits, unit cell lengths of A, B, and C, unit cell angles, that is alpha, beta, and gamma, molecules in the unit cell 4, 18, and 2. This is the cell volume, and this is the true density of the polymorphic forms. Form 2 has the highest density of 1.423 grams per ml. Conformational polymorphs occur when the molecules have different conformations in the three-dimensional space. Organic molecules can have variety of conformations. Different conformations pack to yield different polymorphs, and this is called conformational polymorphism. An example of this is sp-peron polymorphs. Here is the form 1, while this is the form 2. As you can see, the conformation of this molecule and conformation of this molecule are completely different. This gives you a U-shaped conformation, while here you see a L-shaped conformation. These two different conformations will lead to two different polymorphic forms, and that is called as conformational polymorphism. These are the crystallographic features of sp-peron polymorphs. Crystal system in both the cases is monoclinic. This is the space group. These are the unit cell dimensions of alpha, A, B, C, and alpha, beta, gamma. And the unit cell volume is 2085 in this case, and 2045 cubic angstrom in the case of form 2. This classification of packing and conformational polymorphism is somewhat artificial because different packing arrangements impose different conformations on the same molecules, however slight they may be, and different conformations will invariably pack differently. Now we move over to the classification of polymorphs based on the thermodynamics. We will first look at certain concepts involving thermodynamics of the polymorphs. In a macrostate like polymorph, T multiplied by S represents the energy of the system associated with disorder of the molecule. T is the temperature, S is the entropy. Entropy is not just disorder, it is a measure, it measures spontaneous dispersal of energy. Energy spontaneously disperses from being localized to becoming spread out if it is not hindered. E is the internal energy of the system. This is intermolecular structural energy arising from motions of molecules, electrons, and nuclei. It is a sum of individual energies of interactions between the nearest neighbors. There are two components, kinetic energy due to the motions and potential energy due to the position or the bond strength. At constant pressure P, total energy of the phase is represented by enthalpy of the system H. H is equal to E, which is the internal energy, plus pressure multiplied by volume. So enthalpy is the heat required to increase internal energy and perform work of expansion. Gibbs free energy, that is G, is denoted by H minus Ts. H is the enthalpy and Ts is the measure of entropy. That is total heat content minus the bound energy which is unavailable for doing work. Initially, we had mentioned a term macrostate system. A macrostate is a state description relying on macroscopic properties of the system, that is, its temperature, pressure, volume, internal energy, etc. For each macrostate, there are many microstates which result in same macro state. This is the phase diagram of a polymorph. Third law of thermodynamics says that the entropy of a perfect crystalline solid is zero at absolute zero of temperature. This is the curve of entropy. So at absolute zero, that is here, the entropy is zero. Since entropy is zero at absolute zero, G0 is equal to H0, because here this particular quantity will become zero. So free energy becomes equal to enthalpy. This is shown here. G0 is equal to H0. Ts increases more rapidly as compared to H. Here this is shown in this picture. So the curvature in the Ts is more because it is getting multiplied by the temperature term. And this is the increase in the enthalpy along with the against the absolute temperature. Here the curvature is less as compared to the Ts. Hence gives free energy G, which is equal to G is equal to H minus Ts, tends to decrease with increase in the temperature, because this quantity is increasing much faster as compared to this quantity. Hence G will become negative. This is shown by this particular curve here, which is going downwards. Each polymorph yields such a diagram, which is called as the phase diagram of a polymorph. Although values of G, H, and slopes of curves differ between different polymorphic forms. The next system of classification of the polymorphs is based on the phase diagrams of different polymorphs. The significance of thermodynamics of a polymorph is given in this slide. Relative stability of polymorph depends on its free energy. More stable form has lower free energy. In defined set of temperature and pressure, the most stable polymorph is called as the thermodynamic form. since it has the global energy minimum. Global means amongst the all known forms, it has the least energy, while the other polymorphs are termed as kinetic or metastable forms since they have local energy minima. They may be having lower energy, but if we look at all the polymorphs together, only the most stable form will have the global energy minimum. Metastable polymorph is thermodynamically unstable, but it has finite existence. When delta G difference is negative, then transformations can occur spontaneously. And when delta G is equal to 0, then the solid phases are at equilibrium with respect to the transformation. As we all know, when the free energy change is negative, then the reactions are spontaneous in nature. Same concept has been captured here, that when delta G difference is negative, then transformation can occur spontaneously, and when delta G is equal to 0, then solid phases are at equilibrium with respect to the transformation. Based on the relationship of thermodynamic properties of the polymorphic forms, they can be classified either as enantiotropes or monotropes. Enantiotropic systems are characterized by a reversible transition between polymorphs at a definite transition temperature below the melting point. While for monotropic system, there is no reversible transition between polymorphs below the melting point. One polymorph is unstable at all temperatures and pressure. The change is irreversible and goes only in one direction. And the change is always from the metastable form to the stable polymorphic form. A system or certain conditions for identifying the type of polymorphism have been given by Berger-Remberger rules based on the names of two scientists, Arthur Berger and Rudolf Remberger. Here, the form 1 is the high melting polymorph. In the case of enantiotropy, there is a reversible transition between form 1 and form 2 before the melting point of the polymorphs. The transition temperature is less than the melting point of form 1. Form 1 is stable, that is less soluble at temperatures greater than T transition, while form 2 is stable, that is less soluble at temperatures less than T transition. Whichever form is more stable will be less soluble in water. In the case of monotropy, there is a irreversible transition. Transition temperature is greater than melting point of form 2, which means there cannot be any transition in the solid state. Form 1 is always more stable and less soluble as compared to the form 2. There are two rules that are used to identify the type of relationship between the two polymorphic forms: enthalpy of transition rule and enthalpy of fusion rule. Enthalpy of transition rule says that the transition of 2 to 1 is endothermic in nature, while in the case of monotropy, transition from 2 to 1 is exothermic in nature. While the enthalpy of fusion rule says that the enthalpy of fusion, that is delta Hm of form 1, is less than delta Hm of form 2, while in the case of monotropy, the reverse holds true. These rules are for the interpretation of the experimental observation and not a substitute for them. The heat of fusion rule, that is this rule, should be used only if the transition cannot be measured. If the transition can be measured, then the enthalpy of transition rule should be applied. This is the free energy versus temperature diagram, also called as G-T diagram. For the enantiotropic polymorphism, the relative stability of the polymorphs and solvatum forms can be gathered from a free energy temperature diagram. This is the relationship which we have already discussed in the case of enantiotropy, and we will look at it in more detail with the help of this diagram. There are two colored curves that are shown. One is green colored, which represent the form 1 of the polymorph, while the red ones are the polymorphic form 2. These curves are for G, that is the free energy. So this is the free energy curve for form 2. This is the free energy curve for form 1. This blue line is the free energy curve for the liquid phase. That is why it is given by GL. This line is for the enthalpy of form 2, H2. This green line is for the enthalpy of form 1, while this is the enthalpy of the liquid state. So G is the free energy, T is the temperature, T is the transition temperature, T2 is the melting of the form 2, T1 is the melting of form 1, and L is the liquid phase. T1 is the melting of form 1. Obviously, when the free energy of the solid phase meets that of the liquid phase, that is the point where the melting takes place. So this is the melting point of form 1. This is the melting point, while this is the melting point of form 2, because here the G2 meets the GL. Now let us look at the transition from 2 to 1 is endothermic. So this is the form 2, this is the form 1, and when the transition takes place, we are coming from a higher free energy to a lower free energy, which means there is going to be release of the free energy to the environment. Wherever there is a release of the free energy, sorry, just a minute. This is the transition that can take place between the form 2 and form 1, and we are coming from a higher free energy to a lower free energy. So this change is going to be from a higher energy polymorphic form to the lower energy polymorphic form. And if we look at the heat change involved, we can see the corresponding curves of the enthalpy. So this is the enthalpy curve. So we are coming from form 2 to form 1, and from form 2 to form 1 there is a release of the energy, which means the process is endothermic in nature. That is why endothermic, because there will be an absorption of the heat by form 2 to convert to form 1. That is why it will come to a higher enthalpy value. The other rule of the transition is delta Hm of form 1 is less than delta Hm of form 2. Delta Hm is the conversion of the solid form into the liquid form. So this is the enthalpy of form 2, and this is the enthalpy of the liquid. So this is the change involved on melting of the form 2, and this is the change involved in melting of form 1. As is clearly seen in this case, delta Hm2 is greater than delta Hm1. That is what it is written here, that the delta Hm form 1 is less than delta Hm of form 2. So this is the explanation for the inintertropic system based on the phase diagrams of the two polymorphic form. An example of such a system is clopidogrel bisulfate form 1 and form 2. Now we will look at the monotropic system. Monotropic system has these characteristics which we had discussed earlier as well. And these are the overlapped phase diagrams for form 1, which is shown in green color, and form 2, which is shown in the red color. The blue color lined are for the liquid phase. Now here, if we look at the transition from the higher energy form to the lower energy form, then we can see it is happening from uh, form 2 to form 1. And if we look at the enthalpy change involved, we are coming from a higher enthalpy to a lower enthalpy, which means there will be release of energy and hence it is going to be a exothermic change. Similarly, if we look at the delta HM1 and delta HM2, in this case, delta HM1 is greater than delta HM2. That is why delta HM form 1 is greater than delta HM of form 2. The rest of the terminologies are going to be same as we discussed in the previous slide. An example of the monotropic relationship is the polymorphism in a drug called temazepam. Now we are going to look at the phase transformations. A phase transformation or transition is the change of a thermodynamic system from one phase or state of matter to another one. If say form 1 is converting to form 2, we are going to say that the phase transformation is occurring. What is the significance of phase transformation studies? Stresses experienced during processing and interactions with formulation components can result in phase transformations. The behavior of resulting formulation will be influenced by the extent of conversion and the properties of the transformed phase. Therefore, it is important to detect, quantify, and understand the implications of such phase changes on product quality and performance. There are two mechanisms by which the phase transformations can take place. Phase transformations initiated within a single phase. These are solid to solid phase transformation, or the other example is dehydration and desolvation phase transformation. We will first look at this type of phase transformations, that is solid to solid phase transformations. As the name indicates, such transformations take place without intervention of a second component. There is a four-step mechanism that is involved in solid phase transformation. The first step is that of molecular loosening in the initial phase. That is the phase that was existing earlier. Second is the formation of intermediate solid solution. The third step is the nucleation of the new solid phase. And fourth one finally is the growth of the new phase. Even though thermodynamics might favor a solid-solid phase transformation, however, the reaction is kinetically unfavorable and hence some metastable polymorphs can be maintained for years without any evidence for formation of the stable polymorph, because there is an activation energy between the metastable phase and the stable phase. The concept being conveyed here is that although the metastable phase is likely to convert into the stable phase, but this is prevented by existence of an activation energy barrier, and hence spontaneous transformations may not take place unless the activation energy barrier is crossed in some manner, that is by providing energy in some form. This phase transformation will not take place. The thermodynamic relationships between polymorphs can be experimentally determined using the differential scanning calorimetry studies or solubility studies. DSC characterization of solid to solid phase transformation is shown in this diagram. This is the initial polymorph which was existing, and when we heat it in the DSC, the metastable polymorphic form will melt first. This endothermic event is the melting of the metastable polymorphic form. This melting is proceeded by polymorphic transformation as shown by this exothermic event. So there is a formation of the new stable phase which will ultimately melt. So this is the stable forms melting shown by this endothermic peak. So these are the pictures that have been taken by the hot stage microscopy to capture the changes that are taking place during the phase transformations. Dehydration and desolvation phase transformations are also example of solid phase transformation. The transition is caused by dehydration or desolvation process, which leads to the formation of a new crystalline phase. For example, in the case of naproxen dihydrate, if we keep it at 0% RH over a period of 2 days, naproxen monohydrate is formed. And if we dry it at 120 degrees Celsius for 2 hours, naproxen anhydrous form will be formed. Similarly, naproxen dihydrate, if we directly heat at 120 degrees Celsius for 2 hours, it is also converted into naproxen anhydrous. These transitions are frequently encountered in processing consisting of unit processes such as drying, including spray drying, and during lyophilization. The second type of phase transformation is phase transformation caused by the action of a second phase. Two mechanisms exist in this particular way of phase transformation. First one is solution mediated phase transformation, and the other one is phase transformation caused by vapor sorption. Solution mediated phase transformation is abbreviated to SMPT. Solid phase can dissolve in the solvent and crystallize out as a different phase. This is the initial supersaturated solution, which leads to the formation of a form which is the least stable form. This is the second least stable form, and then this is the most stable polymorphic form. One must consider the process from a kinetic point of view than from a thermodynamic point of view, as solubility of solid in solvent significantly affects the rate of transformation. So this is the transformation or the first step of transformation. This is the second step, and this is the third step. So the transformation is taking place from the high energy polymorph. This is having the high free energy. Polymorphic form 1 converts to polymorphic form 2, while it then ultimately converts to polymorphic form 3. This is the least stable form. This is the second least stable form, and this is the most stable form. That is why it is said to have the global free energy minima. The rate and extent of solution mediated phase transformation depends upon the nature of the solvent. Solvent having higher solubility may have higher rate of transformation. Impurities, it may stabilize the metastable form, thereby influencing the phase transformation. Temperature and agitation rate, it may increase the rate of transformation. And hydrogen bond acceptor potential, the conversion rate was found to be slower in solvents that had a greater hydrogen bond acceptor potential. The significance of SMPT lies in the fact that they may attenuate the dissolution advantage of a metastable form, and during wet granulation and freeze drying there may be a formation of new phase, a hydrate or a solvent. So this is shown here. In the spring effect there is a very rapid conversion of the solution mediated phase transformation. So the solubility advantage of the metastable form will be lost and it will become equal to that of the stable polymorphic form. However, if the SMPT is rather slow, like in this case, this is called as the spring plus parachute effect, and it may give us certain biopharmaceutical advantages in terms of higher bioavailability due to the higher solubility. The last type of phase transformations are phase transformations caused by vapor sorption. When interacting with substance in the vapor is water, then product of such transformation of the solid state is a hydrate. For example, conversion of theophylline anhydrate to theophylline monohydrate at a relative humidity of greater than 82%. The partial pressure of interacting component in vapor will generally be the dominant factor in determining the kinetics and type of product formed by sorption of that interacting component. This transformation forms a basis of screening new hydrates or solvent forms of the drug. Dynamic vapor sorption is an effective method to study these type of phase transformation. DVS is used to determine the critical relative humidity for the onset of moisture-induced phase transformation processes. In DVS analysis, the equilibrium water content may experience stepwise jumps when stoichiometric hydrates are formed, which is shown here in this example. At the relative humidity of around 80%, there is a step change in the sorption by the formation of a hydrated form, while the desorption takes place at a much lower relative humidity at around 15% RH. There is loss of this particular water which was gained for the formation of the hydrated form. This is the end of the lecture here. We will be taking up the regulatory implication of polymorphism in a separate class. Thank you very much for your attention.